Hey everybody, here's a lesson on explaining periodic trends. You've explored a little bit about each of the trends and how what the patterns are going across the periodic table, across the period, and down the group on the periodic table. Now we're going to talk about how the atom stays together and how the attractive forces between the nucleus and the electrons can explain some of these periodic trends or patterns that we see on the periodic table. So how does an atom stay together? Now remember, inside of the nucleus are protons. They're positively charged. Outside of the nucleus of an atom is an electron cloud, and they contain the negatively charged electron particles. So what happens is the positively charged nucleus and the negatively charged electron cloud attract. And these opposites, because they're oppositely charged particles, they attract. So opposites attract. Without these opposites attracting, the repulsion between the electrons within the cloud would be so great that the atom wouldn't stay together. So what affects the strength of the attractive force between the nucleus and the electrons in the electron cloud? Well, through the online PhET simulation called Coulomb's Law, you may have discovered that the two variables that affect the attractive force between the nucleus and the electrons, or between two charged particles, is the distance between them and also their charge. So the strength of the attractive force decreases as the particles get further apart. We call this the radius, the distance from the nucleus all the way out to the electron cloud, specifically the valence shell, or the outermost electrons. So as the strength of the attractive force decreases, the radius, or the size of the atom, increases. The strength of the attractive force increases as the amount of charge increases. So here we're describing the particles getting further apart. That goes along with the distance. So further apart, greater distance, decrease attractive strength. Here we're talking about charge. So increase the amount of charge, increase the attractive force between the nucleus and the negatively charged electron cloud. So how and why does attractive force change going down a group? So when we're talking about going down a group, we can think of a periodic table. Okay, we can go across a period or we can go down a group. And so let's take a look at this group that we're going to go down. We're going to go down group 1, lithium, sodium, potassium. We're going down a group. Lithium, 3 protons in the nucleus, sodium 11, and potassium 19 protons in the nucleus. So let's go ahead and let's label that. So we've got lithium, which has 3 protons, sodium 11 protons, and potassium has 19 protons in the nucleus. So attractive force between the nucleus and the electrons as we go down the group is going to decreases. We can see that by looking at the arrows themselves. The arrows are wider and darker, indicating a larger strength of attraction between the electron here in the outer or valence shell, so the valence electron, and the nucleus. As we go down the group, the arrow gets thinner, showing or illustrating that the strength of the attraction between the nucleus and the valence electron is decreasing. So as we go down the group, it's decreasing. So why? Why is the attractive force between the nucleus and the electrons decreasing? Well, electrons are added to new energy levels. So for lithium, electrons occupy the 2nd energy level. But for sodium, electrons are added to the 3rd and even higher, 1, 2, 3 energy level. And for potassium, electrons are added to the 1st, 2nd, 3rd, and 4th energy level. So we can see that here. So the 1st energy level, the 2nd energy level, the 3rd, and the 4th all contain electrons. So electrons are added to new energy levels, increasing the distance between nucleus and valence electrons, causing the force to decrease. So increase distance, decrease force. The inner electrons, which are all the other electrons not in the valence electrons, they are between the nucleus and the valence electrons. So for example, lithium has 2 inner core electrons. However, sodium has 2 and then 2, 4, 6, 8 more. So they have 10 inner core electrons and just 1 valence electron. These inner electrons are called inner electrons, or we refer to them as inner core electrons. What they do, because they become between the nucleus and the valence electrons, they shield, or we call it block the valence electrons from feeling the full positive charge of the nucleus. And because of this, it feels less of a pull from the nucleus. Feels less pull. In effect, the nuclear charge decreases so the attractive force decreases. So as we move down the group on a periodic table, we're adding more energy levels, we're adding more electrons to these energy levels, and the more electrons between the nucleus and the valence electrons, the more shielding that occurs, and so the nucleus cannot hold the electrons in the outer shell as tightly, so the valence electrons feel less of a pull from the nucleus, and therefore the attractive force is decreasing as we go down the periodic table. How and why does the attractive force change going across the period? So now we're looking at sodium, aluminum, and chlorine. So let's look at sodium is in energy level 3, aluminum is in energy level 3, and chlorine. So we're going across the period or across the row. So what happens? So how does the attractive force between the nucleus and electrons change? Well, it increases. And let's take a look at what. Now remember, going down a group, the distance between the nucleus and the valence electrons is increasing and therefore decreasing the attractive force, or the hold, decreasing the hold the nucleus has on its electrons. Here, going across the period, we're not increasing energy levels, and therefore we're not increasing shielding. However, the attractive force between nucleus and electrons is changing. In fact, it's increasing, and I wonder why. So the arrows are showing an increase going across the period or across the periodic table. So the electrons are added to the same energy level. So as we add electrons, so in this case sodium has 1 electron in its valence shell, aluminum has 1, 2, 3 electrons in its valence shell, and chlorine has 1, 2, 3, 4, 5, 6, 7 electrons in its valence shell. So we're adding electrons. So electrons are added to the same energy level. So the distance between the nucleus and electrons is constant. It doesn't change. So it doesn't change, and we say this, it's constant. No change. So the same number of inner electrons, each of these atoms has the same number of inner electrons. The only electrons that are changing are the ones being added to the outer shell, or the valence electron. So the same number of inner electrons, so shielding does not change, because the inner electrons do the shielding or the blocking. So shielding is constant, or shielding does not change. And the increase in number of protons in the nucleus causes electrons to feel more of a pull from the nucleus. So the increase in number of protons, and remember they're positive, causes electrons, which are negatively charged, to feel more pull because they have a greater hold, or they're holding them more tightly. So they feel more pull from the nucleus. So in effect, the nuclear charge increases. So the attractive force also increases. So as the distance between the nucleus and the electrons stays the same, and the number of protons in the nucleus increases, 11, 13, and 17. The nuclear charge is also increasing, and therefore holding the electrons in the valence shell more tightly, resulting in an increase in attractive force between the nucleus and those electrons. So let's summarize the attractive force trends that we see going down a group and across the period for each of these variables. So atomic radius, remember, it's not just the size of the atom, but it takes into account the distance from the nucleus to the valence electrons. That will determine the radius of the atom, or the atomic radius. It's measured in picometers, which is smaller than the atom, so it's small. So as we go down the group, the attractive force, we said, decreases. So AR stands for atomic radius, and the AR will increase or increases down a group because the attractive force decreases. And the electrons are not pulled in as much. Also, there are more energy levels as we go down a group, making the electron cloud bigger. And therefore, the valence electrons are just further away, decreasing the attractive force between the nucleus, and therefore the electrons will feel less pull. They won't be pulled in as much, so the size of the atom is smaller. As we go across the period, however, the atomic radius decreases across the period because the attractive force is increasing. And the result is electrons are pulled in more. By increasing the number of protons, so increasing number of protons. We're increasing the nuclear charge. We're increasing the nuclear charge of the atom, which gives the nucleus more of a pull on electrons. So without changing energy levels. So increasing the number of protons increases the nuclear charge without changing energy levels. And therefore the nucleus has more of a pull on electrons. And the atomic radius is smaller because the electrons are pulled in more. The ionization energy is the amount of energy required to remove the first electron from the valence shell. So the IE, or the ionization energy, decreases because attractive force decreases. The valence electrons are more loosely held or they feel less pull from the nucleus. And therefore, it takes less energy to remove the electron, to disrupt, force, and remove electron from its outer shell. As we go across the period, across the periodic table, the pattern or the trend is that the IE, or the amount of energy, the ionization energy, the amount of energy required to remove an electron, increases because the attractive force increases. The valence electrons are more tightly held. Or they feel more pull, from nucleus. And therefore it takes more energy to remove an electron. So when we talk about removing an electron, or if the atom has to gain or lose an electron, by removing an electron, we're talking about the electrons being lost and whether it's easier or not. And now instead of saying it's easier to lose one than gain 7, we say it requires more energy to remove 3 electrons than it does to remove 1 electron. So that's the ionization energy, the amount of energy required to remove an electron so that the atom can achieve stability. Electronegativity is the ability of an atom to attract electrons. So if we think about an atom, it has a nucleus. If we think about another atom, a different atom, it has a nucleus, and they might be sharing electrons, each one with a negative charge, in order to achieve stability. And so we're talking about that attraction between the ability of that nucleus versus this nucleus to attract that electron from the different atom in this shared or covalent bond. So the tendency to attract that electron is referred to as electronegativity. So the electronegativity decreases because the attractive force decreases. In other words, the nucleus can't pull electrons in as well. And therefore, the atom has less ability to attract other negative electrons. As we go across the period, the attractive force increases. So the tendency of the atom to be able to attract a pair of electrons increases because the attractive force increases. As a result, the nucleus has more pull on electrons. And therefore, the atom has more ability to attract other negative electrons. So let's review. As we recall, metals typically lose electrons to become stable like a noble gas. Looking at the amount of energy required to remove an electron, or i.e. for metals, explain why metals typically lose electrons. I'll look at metals on the right side of the periodic table. They have lower ionization values, and lower ionization values means it's easier or less energy is required to lose electrons. Let's look at sodium, magnesium, and aluminum, for example, and I'm going to restate. The metals on the left side of the periodic table have less ionization energy, and less energy is required to remove one electron versus 2 electrons versus 3 electrons. So as we move across the periodic table, more energy is required to remove electrons. So greater ionization energy, and therefore IE, or ionization energy, increases as you go across the periodic table because the nuclear power, or attractive force, is increasing. So metals on left side of PTE have lower ionization energies or require lower amount of energy to lose electrons. So this means less energy required to remove electron or lose an electron to become stable like a noble gas. So what group of metals is the most reactive on the periodic table? So if you look at the periodic table, which group is the most reactive and therefore requires the least amount of energy to remove an electron? That would be group 1. Group 1 is the most reactive group of metals on the periodic table. Because less ionization energy is required to remove an electron. In nonmetals, which by the way are on the right side of the periodic table, in nonmetals typically gain electrons to become stable like a noble gas. And looking at trends in electronegativity for nonmetals, explain why nonmetals typically gain electrons. Well, nonmetals, which are on the right side of the periodic table, have the highest electronegativity and therefore have a greater ability or tendency to attract electrons. So nonmetals, right side of PTE, have higher electronegativity values and attract electrons more easily. What group of nonmetals is the most reactive on the PTE? What group? Well, group 17, because they only have one electron to gain in order to be stable like the noble gas, so group 17. What makes noble gases in group 18 especially stable? Well, if you look, noble gases have 1, 2, 3, 4, 5, 6, 7, 8, with the exception of helium. The rest of the noble gases have 8 valence electrons or a full valence shell. So 8 valence electrons to be stable. So how would you describe the electronegativity of noble gases such as Ne and argon? Well, electronegativity is the tendency to gain a pair of electrons. And because they already have 8 valence electrons, they are stable. And so their electronegativity value is 0. 0 tendency to gain a pair of electrons. So 0 En. So that's how we explain periodic trends in terms of attractive force down a group and across a period, and how we relate it to the distance between the nucleus and the electron cloud, as well as the charge as it relates to the attractive power between the nucleus and the electrons.